and so on in this language, but that's not what I'm going to get into. I just want to make the point that I can orient the lattice in this way, and that the two the two basic actions in the diagram. So now I have tended to draw things, the matrices acting from left to right, and represented it by some vertical action, but sometimes I do it horizontally instead, if you allow me. So this means that now in this new representation I have strings and I act on them like this and so on, right? Then these diagrams can be, every node can be split in two ways, either like this or like this. This represents the identity, this represents temporally lib. I have not added any degrees of freedom because I am not summing over orientations. The point of the orientations is just to suggest something. What is it suggesting? This orientability. It is suggesting that we could yet find another representation of the temporally lib algebra, and that's the one that's going to be related with the simple loop model. So the simple loop model on the torus is a model of orientable loops, which means simply that they come, the non-contractible loops come in even numbers, and everybody has fugacity the same, n. Okay, so that's the simple model. And the point I want to make now is that thanks to this orientation, I can imagine a new representation of temporally lib that will exhibit the UN symmetry, or SUN symmetry. Yes? Can you start from the beginning? In the POTS model? I didn't explain it in great detail. I just said that because the correspondence between non-contractible clusters and loops breaks down, we would have to change something about the fugacity of the non-contractible loops. I didn't say any more on this. I can if you want, but for now maybe we can leave it as is. So, what's the idea now? Well, the idea is that the orientations of the lines will be associated with different representations of the SUN algebra. So we're going to associate with an arrow pointing like this, we're going to associate the fundamental representation of SUN, and with an arrow going like this, we're going to associate the dual fundamental representation of SUN. If you don't know what this means, let me anyway write it down explicitly. Sometimes I will also, instead of this, use this notation. But let's write them down explicitly so there will not be any problem of understanding. So to do this, we're going to introduce yet a new model. I told you about XXX, about this, I told you about spin SU2, which was a model with 2 states per side. I told you about the POTS model, which has Q state per side. Now we're going to introduce yet another model, which will have UN symmetry. So we're going to do it as follows. For these representations, we're going to introduce a bunch of bosonic oscillators. So I'm going to call them BIA and BJB dagger. So we're going to have delta IJ, delta AB. So this means for each, if I have a line like this, now I have, let's use boxes. A box, box bar, box, box bar, box, box bar. So the space on which the transfer matrix is acting is now the tensor product box times box bar to the power m over 2 equals n, as usual in my notations, right? So for each of these, they will have a label I, which I'm going to start with I equals 0, I equals 2, I equals 4, and so on. The even labels will correspond to this. So I even. So what I mean simply is that for each I even, I have a collection of n bosons which commute if the two sides are different, and if the two sides are not different, if they're identical, then I have a simple commutation relation of this type. And for box bar, I'm going to have something very similar, but I'm going to use a slightly different notation, b bar ia, b bar j, b dagger. So it's a little bit clumsy, but yeah. I'm not going to be too careful with the position of the indices, though I should. Okay, so this is going to be our bosons on the odd sides. So of course, for now, I have now infinite dimensional representations on each side, because I could have no boson, one boson, two bosons, three bosons, and so on. And on top of it, I'm going to use constraints. So I'm going to constrain or reduce the Hilbert space if you want, so that b dagger ia bia equals 1 on even sides, sum over a implied, and b bar I a dagger b I a bar equals 1 on odd sides, right? In other words, I'm restricting myself. It's a very fancy way, quite common in condensed matter physics. I think probably, well, I learned this kind of thing from Jan Affleck, but I'm sure many people have worked on this before. We simply have on every site n possible states. Okay? I could. What's really fun is to put bosons and fermions. And then you can have super unitary symmetries. I could put fermions. I like bosons myself, but it doesn't matter. It's just a convenient way of getting a representation across with explicit expressions for generators. It's not particularly important, but I like to do it. Not the only one who likes to do things this way. So anyway, I can do that, right? So I have on the even sides, what I mean is simply I have n possible states, and on the odd sides, so I have on even sides, I have n possible states, which I write as bi a dagger acting on the vacuum, right? With a equals 1 to n. And similarly, on the odd sides, I have n possible states. That's all I mean, okay? Now, what is the advantage of doing this kind of business? Is, well, it is useful for several reasons, but one of the nice things is now you can explicitly, in this language, quite nicely write the Temple ellipse generators and the UN generators, which otherwise would be a little bit more annoying. So first of all, for now I have not mentioned UN except to tell you that I was taking spaces of dimension n, but now I can write the generators explicitly. So for I even, I'm going to define JIAB as B dagger IABIB, and for I odd, GIAB, and I'm being careful with the positions of the indices, B dagger I dagger B, B bar I A. Okay. So on even, I kill a B, I create a A. On odd, I kill a A, I create a B, and I put a minus sign. Okay. That's my definition. And then I said JAB is sum from I equals 0 to, so in these notations, M minus 1 of GI A B. Claim these generate SUN or UN, or I should say rather, they obey defining relations of UN. That is, we have JAB, JCD is delta AD ABC, delta BC, JAD minus delta AD, JBC. So we're having a nice way to build the UN symmetry acting on this system. And it's nothing else but the generalization of what you would do with the XXX chain, although I haven't yet defined the interaction, and spin a half, only instead of 2 colors, you have n colors, right? So even if you don't know anything about UN, this is a completely well-defined construction. And now, the important result is that we can introduce yet another representation of the Temple-Elib algebra. Let's see, maybe I should erase up there, in fact. So, yet another representation of the Temple-Elib algebra. And that one should be pretty simple, because remember, what we said is, oh, okay, we're having something like this. And then we can have either this diagram or that diagram. And now, because of our bosons, we can really think of the lines as carrying a boson. Remember, each line gets a fugacity n. Hey, n for n colors. So now we can think of the loops as carrying a color. And this is, now remember, we're acting, our action, matrix action corresponds to moving horizontally. So this is the identity. I have a bunch of bosons coming and they come out just the identity. This is a contraction. What do? I identify these 2 colors and I allow 2 bosons to come out which should have the same color. In other ways, I can write EI is B bar I plus 1 A dagger B I A dagger B I B B I plus 1 B bar. So this corresponds to I even. What does this mean? I sum over A and B. So what does it mean? So this is even, it carries a B. This is odd, it carries a B bar. I take the B and the B bar that come with the same color, tac tac, I contract them and I create a pair of what? A bar. Right? So I annihilate a pair of bosons, I create another pair of bosons. This is what I do for the even sites. For the odd site, it's completely the same, but reversed. I must simply exchange the bars and the non-bars. Okay? Okay? Same thing otherwise. So now this is odd, and this is even. So in this language, It's really quite beautiful. We're having a temple-ellipse action. So why is this temple-ellipse, by the way? There's a quick way to prove it. Use diagrams, right? Because this is doing nothing but annihilating a pair of colors and creating sum over A and B implied. So what does this mean? Maybe I should spell it out. It means that EI, let's take I even. Let's take I even. So EI acting on a state which I will represent as C and D bar. C is from 1 to n, D bar is from 1 to n, but now I use the color with a bar to denote the fact that I am on an odd site. Well, this is a sum over B, so it forces C to be equal to D. And then it's also a sum over A, so that's sum over A of A bar. That's what it is. I annihilate identical colors and I create a pair of identical colors. How about EI square acting on CD bar? Well, that's delta CD EI acting on sum over A of AA bar. For each A, EI acting on AA bar is what? EI acting on AA bar is sum over, I don't know, BB bar. Every time the sum runs from 1 to n. So that's n, delta CD sum of BB bar, which is n EI CD bar. So E square is NE, which I really don't have to do this because the diagrams show it for me. I take two colors and I act with EI. If they're different, that's 0. If they're not different, they're equal. Then I contract them and I create a sum of all the other colors. Which, of course, if I repeat that, I get a multiplicity n because I had n colors. So E square is equal to n times E. Yes. Yes. From the commutation relations. You mean of the B's? Well, if I write, so remember we have the constraint that we're acting on states that contain one particle. So if I have a certain state with B, okay, let's yeah, B, what can you do? Okay, A, I can destroy it. So what you mean is you're worried because I go out of the one particle Hilbert space? Is it what you mean? Okay. So well, maybe I'm not sure I understand that. Well, what this means is simply I'm acting on a pair of states, I mean on a state with two bosons, one carrying the color A, one carrying the color B. One is without a bar, the other one is with a bar, and I destroy them both and I replace them by a pair. I don't need to do algebra to see it. So if you're bored this afternoon, you can prove EI plus 1 EI equals EI, not with diagrams, but laboriously like this. You're welcome. Of course, you'll find the same result in the end. It is yet just another representation of the temple-ellipse algebra. And now, of course, because of all this construction, it should be pretty obvious, and I would like to leave it as an exercise, that these generators commute with the action of UN defined like this. In other words, and now it is totally explicit, so hopefully it is somewhat answering some of the questions for n equals 2 that I discussed earlier, because of course, when n is equal to 2, the fundamental and the conjugate are in fact the same for SU2, so we can use all this for SU2. So claim JAB, the generator of UN, commutes with EI for all i's. So it is a model with UN symmetry. And finally, I can, and I will, close it onto itself, right? I didn't quite say this explicitly so far, but remember, because the orientations are perfectly compatible, what I'm going to do finally, okay, is decide that this guy and that guy can be contracted with one more temporal ellipse generator, which I will call E0. So, no, I have an E0 already because I started at I equals 0. So it is going to be EM, the last temporal ellipse generator, which means that in terms of diagrams, now if I have a bunch of strings propagating in this configuration, for instance, not only can I contract here, 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 or there, the EIs I've defined so far, but I can also do this. This is the action of the last generator that I define like this. And because the loops, the fugacity of the loops comes simply from the number of bosons that can propagate on it, I have a loop model where now all the loops should have the same fugacity n. So the so-called UN loop model is the model with, in fact, all loops having fugacity n and systems have an even number of sites in both directions. That's the model on the torus, which is just a way to say that the loops are orientable in the way I defined earlier. So this is what's called a UN loop model, and it will correspond to a different universality class from the SQ POTS model. Okay? Yes? It contracts the last string and the first string, the last color and the first color. So far, we didn't have any such thing. So far, we defined only contractions between neighbors. But now on the torus, I can consider the last one and the first one to be neighbor. And because the number of sites is even, the last one and the first one are opposite colors. They are odd and even. So I can contract them. That's what it's doing. Yeah. Oh, I'm sorry. Thank you. Okay, so we're having a model with SUN symmetry, or UN symmetry, and then I want to go back to commutants, because it is absolutely fair to ask oneself, okay, this representation of the temporal ellipse algebra, fine, we're going to study it as a loop model very soon, calculate exponents and all that, I hope, but for now we can still do a bit of algebra. We expect, what do we expect? Well, we expect that we're having a space, so our space is the tensor product 1 times 1 bar to the power m over 2 equals n. And what do we expect from a space like this? if we have an interaction that commutes with the symmetry. So first of all, as a space, as a representation of UN, it should decompose over representations of UN coming with some multiplicities, right? That's an easy exercise, which I'm not going to do now. I may do it later, but for now, let's just think of it abstractly. For instance, just as an example, if M were equal to 2, I would have the tensor product of the fundamental and its conjugate, which would decompose as a sum over the trivial representation and the adjoint representation. If I had more, it would be more complicated. I don't really care about this for now, because I also know that my Hamiltonian commutes with the Temple-Elib algebra. So I can also write this as a sum from j equals 0 to m over 2 equals n. So let's do it in the open case for now. We'll think about the periodic case later. Let's focus about the open case here, just to be able to compare with what I did earlier. So we know that we have our representation of the Temple-Elib algebra. They're always the same, independently of the lattice model I use. There are all the irreducible representations of the algebra, so I must be able to write this space as a decomposition involving these guys times some multiplicities, times something that commutes and I can even be a little bit more precise. I could, for instance, ask myself, okay, how about decomposing n squared to the power m over 2 equals n, which is n to the 2n. How does it decompose? Well, it would decompose as sum from g equals 0 to n of the dimensions of these guys, which are the dj's, times some multiplicities. This is what I expect from the space in general. And now when you think of it a little bit, you realize that the only way to have these two decompositions hold at the same time is that the multiplicities, and I will explain this more next time, but I want to give you a preview, these multiplicities will only be possible because of this alternative decomposition. This is only going to be possible if the multiplicities correspond to putting together many representations of SUN, which therefore will have the consequence that the commutant algebra of the Temple-Elib in this space will have to be something else than UN, something much bigger than UN. So the commutant of Temple-Elib must have representations that are mixtures of UN representations. And this will imply that the commutant is larger than UN. And that's one of the reasons why it's interesting for people doing, in particular, thermalization issues in some of these problems, is because if you have things that commute with your interaction, because EI is the interaction, right? If you have things that commute with the interaction that are larger than a known local symmetry group action, this is going to lead to more conserved quantities and therefore maybe or maybe not thermalization. So this issue of the commutant of the temporally algebra in this system is a very important issue, and I will get back to it later on. I know it sounds a bit mysterious, but I thought I would mark the point here, and then later on, hopefully, we'll be able to say more about exactly how the UN representations get mixed together into much bigger representations and what kind of symmetry is hidden behind these models. Okay, so that was just an aside. If you don't really fully get it, that's okay. Okay, 10 minutes before the end, it's good, I'm roughly on time. So maybe one word about conformal field theory, just one word. I will not go very far today, but Potts model is the SQ model. The theory we are looking after is a field theory that somewhat would make sense for Q arbitrary. Well, it's a little hard to imagine what this theory is. You would need to know more than what I've said so far, so let me not get into this so much. Let me get into something a little bit easier. What about UN? So now that I have my model, if it so happens that the model is critical, but we know it's critical because up to these details about the topology, it is pretty much the same as the Q-state Potts model, which we know is critical as defined as a dense ensemble of loops, and it has some universality class. So certainly these models should be critical for n between -2 and 2. So we expect to have CFTs with UN symmetry, whatever that means, for n between -2 and 2. Okay. By the way, UN is a continuous group, which means there should be currents in this system, which is some interesting question. It's a big difference with SQ. SQ is a discrete group. We don't expect currents in an SQ theory. So expect to have CFTs with this symmetry, and it so happens, so there's a conjecture that the CFT is it's the complex projective sigma model, CPn minus 1 sigma model, at theta equals pi. This may not mean anything to some of you, I'm really sorry. I don't want to get into it now, I just want to also first throw it and see what you do with it. But complex projective sigma models are just sigma models on some simple targets, which are pretty much quotients of UN by U1. And then there's a topological angle, and this is a generalization of something else that maybe you know, generalization of the fact that the XXX spin chain for an even number of sites, careful, flows to the O3 sigma model at theta equals pi, which flows itself onto the SU2 Vesumino theory at level k equals 1. So again, if you're not familiar with these things, this is essentially Chinese, no offense meant. But if you do, it should tell you something. Okay? So the point is there are natural field theories associated with the SUN or UN models, not so much for SQ. It's not that it's not possible, but it's particularly unpleasant. But I think this would require more work. But in the few minutes I have left, I want to finally tell you about the last model, the model with ON symmetry, and maybe this model will be more familiar to you than any of the other models I have introduced so far. So we've had the SQ, we've had the UN. As if it were not enough, I'm going to invent yet one more model, the ON model. Okay, so bear with me for 5 minutes. Let's go a quick dirty derivation of what the ON model could be. So the ON model would be a model of spins. So we would take a lattice. We're going to take the honeycomb lattice because it's so cute. We're going to take the honeycomb lattice, and then the partition function of the ON model would be something like where we would need to integrate over all the spins. We would put spins on the vertices. Now, spins with ON symmetry, that means SI would have n components. And maybe we could take these guys to have norm n square. So we would integrate over all these spins. This would be an isotropic measure on the n-dimensional sphere. And then we would take product over the neighbors of e to the k sj dot sk. This would be a natural model to define the ON model, right? UN is more complicated because, well, you have this business of complex conjugation that enters the game. That's why ultimately you end up with the projective sigma model. So let's think of this, it's simpler. Now this, you could say, let me do a high temperature expansion, just like we did for the Ising model. Fine, you could do that, but it would be horrible, because in the Ising model, sj.sk was 1 or minus 1. In this case, sj.sk is just a mess. So the smart physicist said, oh, well, you know, maybe I can replace this by a simpler model where z would be the sum, and instead of taking e to the k as j.sk, we're just going to take 1 plus k as j.sk. So we're going to replace the exponential by just the first term. When doing this, we are oversimplifying the model, but we are keeping the crucial fact that the model is ON symmetric and that the model favors spins being aligned, right? So it so turns out that this model is believed to be in the same universality class as that one, something that I will try to justify later on when we'll have solved this theory and we'll know the dimensions of the various perturbations, and we'll be able to argue that the ones that correspond to going from here to there are irrelevant, even though it's only perturbative. But anyway, but let's for now take this model, and now we can do the kind of game we've done many times before. For every edge, we take a 1 or a k, so we get loops. So we're having one more loop model, my goodness, one more loop model, where now we start drawing loops like this. And like in the Ising case, we can argue that if we have a dangling spin, the integration over the sphere gives us 0. And if we have loops, then the integration gives us a factor n. So this partition function can be written exactly as a loop model on the honeycomb lattice k to the b and to the l. But it's not exactly the model I've been playing with so far, because the model I was playing so far is fully packed. This one does not have to be fully packed. So point number 1, this model is what we call, in general, a dilute model, that the universality class I was mentioning at the beginning. If k equals kc, we get the dilute critical model, point number 1. And point number 2, it's not the same as the UN loops, because the loops for ON are not orientable. So the main point is now the loops are not orientable, because I can have on the torus, so let me take once again my stretched torus, I can perfectly well have a configuration like this, no? Nothing prevents it, where I have, so this is the stretched version of something like this. The diagram that's perfectly allowed in this expansion, but now you see it's not orientable, because if I try, I'm going to put an arrow like this, an arrow like this, an arrow like this, and I'm going to enter a contradiction. So the difference between UN and ON is quite small. It all has to do with orientability. So finally, now we can finish our classification. We have SQ models, UN models, ON models. And they differ by the fact that here there's a question of orientability. Here there's no orientability. And here it's more complicated because we have to take into account non-contractible loops. I've not really told you how to deal with that, but at least conceptually you know that it's there. And then for each of these models, we can either take the dilute critical point. So here that would be K equals Kc. Or the dense phase. The dense phase, like I discussed at the beginning, would be K greater than Kc, where we force many loops in the system. But if the symmetry remains ON, we may force them all we want. They will not be orientable. So we have 2 here, and 2 there. We have 6 CFTs to solve. And they're different, they're really different, related to each other, of course. In a certain sense, this is a sort of orbifold of that one, and this is a sort of this one is also an orbifold of that one, in a certain sense. But nonetheless, conceptually, we're having these 6 theories to solve. Last point, just to conclude with one word of physics. All this business should not make us forget basic ideas of physics. One of them is, why would we have a phase transition in the ON model? I've told you for n equals 1, the phase transition we were talking about is the transition between ordered and disordered. We know it exists for the Ising model, but if ON is a continuous group, we are in principle prevented from having a critical point by the Mermin-Wagner theorem. So remember, in 2D, the Mermin-Wagner theorem, which is really a fancy word for a simple idea, Mermin-Wagner theorem tells you that you cannot spontaneously break a continuous symmetry So this would suggest that if I take an ON model and lower the temperature, I should probably not encounter a phase transition. The only exception to this is n equals 2, where we're having the Kosterlitz starless phase transition, but this phase transition does not correspond to breaking the symmetry, and it has a low temperature phase that's critical. It's really quite different from the sort of phenomenology we are looking after. The phenomenology we're looking after is inspired by the Ising model. It has a high temperature phase, a low temperature phase, a critical point. We would expect that these models would behave like the Ising model. How can they behave like the Ising model if the Mermin-Wagner theorem prevents them from doing so? Well, it's because this theorem holds only for unitary theories, which means essentially theories that are defined by a local action with well-defined local variables and positive Boltzmann weights. And now when we do this continuation from n integer to n real or n complex, we're entering a jungle. We're entering a jungle where, in particular, we do not have any constraint of unitarity. So it so happens that the ON model, defined in this way by analytic continuation, does experience a spontaneous symmetry breaking when you lower the temperature. And that's shocking, but it is not forbidden, again, because of non-unitarity. So what we are discovering here is something that you haven't quite really perceived yet so far, is that non-unitarity makes things difficult and interesting. Makes things difficult, but very interesting. In particular, we can have, like I said, spontaneous symmetry breaking in the case of ON when n is smaller than 2, and many other properties. And the reason why it's interesting is because, well, it's also difficult. So non-unitarity has a lot of consequences. Some of them are nice, more physics happens, but some of them are quite difficult, and we will find out about some of them later on. And as you know, final remark, non-unitarity and non-hermeticity, which were taboo up to 20 years ago, now have become the mainstay, lots of papers, lots of experiments. So it is not as unphysical as it may sound, although of course in this context it's not quite the same story. All right, thank you for your attention.